Assalamualaikum. My name is Muhammad Syatibi Ghazali bin Muhammad Zahruddin. Today I'm going to present about linear DC machine. Okay, so far in this I will explain about their basic definition classification, then the various operating principles such as Faraday law, Lemming rule, and also about energy conversion principle involved in electrical machine and all the related concepts. Video, we are going to study a concept which will be very helpful in understanding the operation of electrical machine, especially the DC machine speed of DC motor or generator. Okay, so first, what is a linear DC machine? Okay, a linear DC machine, it has the same operating principle and exhibit the same behavior as that by motors and generator. It is a good way to understand the basic concept associated with the construction and the working of. Okay, as you can see, this is the picture of a linear DC machine. Okay, we go to the next slide. Okay, construction of a linear DC machine. Okay, so the basic arrangement of a linear DC machine, it consists a battery which is connected through a switch. Okay, a small frictional conductor is placed is a constant magnetic field. In that vicinity, the conductor is placed. So the diagram look like this. Okay, this is the supply voltage, the battery. This is the switch connected to a resistor. This is the conductor of length, which is placed a magnetic of flux in of flux density B. Now, in order to understand this operation, we have to take the help of a certain mathematical equation, which is based on Faraday and a Fleming's rule. Okay, for the next slide. Okay, so there in this linear DC machine is a number of equations involved related to the various aspects. The first equation is for the force acting on the conductor, which is placed in the magnetic field. Now, if you remember, Fleming's rule is that it has two statements. Okay, so the first current carrying a conductor placed in a magnetic field experience a force and tend to rotate. For the second statement, is a moving conductor or a rotating conductor is placed in a magnetic field, a voltage will be induced if a current flow through it as a result of that voltage is induced. So, according to the first statement of Lemming rules, the force which it acts on the conductor and tend to rotate the conductor, the magnitude of that force or the mathematical expression on that force is a given F equal to BIL, whereas capital B for magnetic flux density, I current flowing through the conductor, L length for the conductor. Okay, next is the second statement is a moving conductor in a magnetic field as a result of that voltage is induced in that conductor. So the expression of the mathematical expression of the induced voltage in the moving conductor in the magnetic. So the expression of the mathematical expression of the induced voltage in the moving conductor in the magnetic field is given by VBI. V is the velocity of the angular velocity or the velocity of the rotating or moving conductor in the magnetic field. And B is the magnetic flux density, I is the length of a conductor. This is the expression for induced. So this is the expression of induced voltage. So if we apply the KVL equation applied to the linear DC machine, it will look something like this. Okay, VB minus IR minus E induced equal to the 0. The battery supply is a voltage. Okay, so VB is a stand for supply voltage, R is a stand for resistor connected. Okay, for the next slide. Okay, then another equation is for the force with the conductor move. Now, as the conductor rotate, there will be a change in velocity, which will lead to acceleration. And we know that the force is equal to mass into acceleration. So F net is equal to ma. So this is the equation for the force. Because of the moving conductor, it accelerates because the change in velocity. So this is the equation for the force because of the accelerating motion. Okay, so we look, the m is equal to mass of the movable conductor. A is stand for acceleration of the moving conductor. So these are four equations that are involved with the respect to the linear DC machine. First, the force acting on the conductor in the magnetic field. Next, the expression of induced voltage because of the moving conductor. The KVL equation applied to the linear DC machine. And the force because of the accelerated motion of the conductor. Okay, we will go to the next topic, behavior of various parameter versus time. So, there are various graphs associated with the various parameter with the respect to time. So, first, this is the plot between velocity and time. Now, we know that initially the bar was at the conductor, bar was at the rest. So, velocity was a 0. Okay. So, C at t equal to 0, the velocity is a 0, then it acquires steady state velocity. So the steady state velocity VSS is equal to VB by BL. If we take BL to the left hand side, it will come to the denominator. So the steady state velocity will come cap B by B. So I see the steady state B by B, and so this is the plot of velocity with the respect of the time. Okay, next for the induced voltage, the same thing almost for induced voltage at start. When the bar was initially at the rest, the induced voltage was a 0 because velocity was a 0. Initially t equal to 0, the induced voltage is 0. As time progresses, the induced voltage start to increase and gradually it become this is the maximum value equal to the battery supply voltage, which is VSS BI. So the maximum value of the induced voltage VB equal to VSS BI. This is the maximum value of the induced voltage is VB equal to VSS BL. This is the steady state induced voltage. Okay, we go to the next slide. The next parameter is the current with respect to time. Here it follow the opposite thing. It goes from maximum to minimum, and it goes from minimum to maximum. You see, from the maximum to the minimum, high to low. And start the current because the induced voltage was a 0. If we put E induced 0. Here, the initial current was a VB over R maximum. Now, as the induced voltage start to increase, the current start dropping. So, pay attention to this equation here and this equation. If we substitute the E induced D0, it becomes VB over R, the initial current. Then, as a current started to induce voltage increase with respect to time, the current start to drop. So this is the maximum VB over R, then it start to drop to almost C. Okay, the next parameter is the force. So this is the force. It is dependent on a current because the induced given is given by BIL. So the initial, as the current drop, the force also drop. So it follow the same trend as a current. So see, the induced voltage follow the same nature as the velocity because the induced voltage. So both this curve, induced voltage and the velocity, they follow the same nature. Now the force acting on the conductor and the current, they are dependent on each other through this equation. So they also follow the same pattern. Okay, so for the conclusion, a force F load is applied opposite to the direction of motion, which causes a net force net opposite to the direction of motion. And as we can see, this is for the conclusion we made. An amount of electric power equal to E induced current is now being converted to mechanical power equal to F induced voltage and the machine is acting as a motor.